series on the Intel SGX technology. Today's lecture will focus on the basics of SGX, including how it works, its applications, and so on. And in the next class, we will study one application in detail, in particular, how SGX can be used to protect containers, in particular, things like Docker containers, which you may have heard about. Okay. So today's lecture is called SGX and Enclaves. Okay, so let me introduce this subject by talking about a problem, which is a fairly important and real world problem that many clients of cloud computing face. So let us say that you're a client of a cloud platform, right? Maybe you want some credits on Amazon, and you want to uh, run your computations on Amazon because you want to get the benefits of cloud computing, okay, which is scalability, not having to procure and maintain hardware platforms at your end, and so on. Okay. The only concern, though, is that you have some sensitive data, uh, and this sensitive data may be things like trade secrets. Maybe you're running a business, trade secrets, and you don't want to give it to anyone, right? Um, you don't want to give it to obviously your competitors, but you don't even entrust the cloud provider with this data. So here's the problem, right? Now, if you take your data to the cloud, for example, if you want to run some data analytics on it, the cloud provider, the way that they will do it is that they will put it in a virtual machine or a container. That is the standard execution abstraction on the cloud, and they will run computations on it. Now, the problem is that the cloud provider's infrastructure has a complete view of everything that is going on inside the virtual machine or the container. So that's what this picture here shows. Here is the virtual machine that's been assigned to you, and it stores your secret data. And here's the cloud provider's hypervisor. It runs on top of the cloud physical platform. The hypervisor has full visibility into what's going on inside the virtual machine. Why is that? Well, at the end of the day, the virtual machine is nothing but a virtual address space. The virtual address space of this virtual machine is managed by the hypervisor. And all of the virtual machine memory of this virtual machine is backed into the physical memory that is controlled by the cloud provider. Therefore, the cloud provider can just peek into the memory and look at all of the contents running inside the virtual machine. Of course, you'll have to interpret it, but the point is that that's just some additional work for the cloud provider. But the crux of the matter is that your secret data is gone, right? It's now available to the cloud provider, and that is against your security goals. So I've drawn a picture here with the virtual machine running on top of the hypervisor. The story is exactly the same if you were to consider a process and an operating system. Okay, it's exactly the same. The operating system has a complete view of whatever is going on inside every process. That's again because the operating system manages the page tables for the processes, and also the operating system can go and read the physical memory that backs the virtual machine memory of each process. So as a result, you are implicitly trusting the cloud provider not to do something like this whenever you take your computations to the cloud. Now, unfortunately, this notion of trusting somebody, trusting a cloud provider, be it Amazon or be it Windows Azure or be it the Google Cloud Platform, that is not an acceptable situation. That is not an acceptable situation in many, many business cases. So, for example, banks are extremely sensitive about the data that they store. Insurance companies, trading companies like Goldman Sachs and all of these companies that store a lot of sensitive client data, trade secrets. These are companies that just don't want to take their computations and take them to a public cloud like Amazon or Microsoft or Google Cloud. Okay. The problem is that, even if the cloud provider like Amazon, right, maybe they are a trustworthy entity, and you want to believe that their reputation will prevent them from doing something bad. The problem is that the cloud provider, in order to maintain the cloud, they employ thousands upon thousands of cloud administrators, and each one of them has administrative access into this layer over here. And as long as they have control over this, they can view what is going on inside. So, what is the basis of trusting all of these malicious employees? There is no basis, right? And why would a bank choose to compromise the integrity of their business? Or a hospital, why would they compromise the integrity of their patient records to somebody in the cloud providers payroll, who can monetize this data and sell it to their competitors for a lot of money, right? There is no reason to trust these people. All that we have right now is the word of mouth, saying, or a verbal assurance saying that we will not misbehave. But what is to trust that? How do you enforce that trust? That's one part of the story. The second part of the story is, government subpoenas. Many a time, many governments want to monitor what's going on. So let us say that you are taking your computations, and you are running it on Amazon. Amazon is running data centers worldwide. Maybe there's a data center somewhere in an enemy country, who doesn't have friendly relations with us, and they want to see everything that is going on inside your virtual machine, inside the code and data that is being sent from, let's say, another country. And government subpoenas, if you're running a data center there, the cloud provider has absolutely no uh, options there. They have to give in. It's almost like how they bug telephones, right? If the government says, I want to bug this person's telephone because I want to monitor their activities, I suspect they're doing something wrong, the telephones department has to comply. Exactly the same way, the cloud provider receives a government subpoena saying, hey, monitor what's going on over there, then they have to, right? It's a government order, otherwise they have to shut shop in that country and move on. So you might want to protect yourself from such government subpoenas, and therefore you might not wish to take your computation to any cloud provider where the hypervisor, or the cloud provider in this particular case, has full visibility into your virtual machine. This is a big reason why banks, financial houses, hospitals, and so on do not adopt public cloud computing. Rather, they build their own data centers, and they have their own sort of private cloud setup in which they do their computations. They do not rely on public cloud platforms. Okay, so this is a big problem today. So, how can we solve this problem, right? Is there absolutely any hope for the client to keep their data private on a cloud platform? Okay, so you might think that encryption is the problem, right? Maybe the client can just encrypt the data on their end and send it to the cloud provider. Well, that's not a good solution. The reason is because if you've got some data, let's say M, maybe this is, you're talking about a hospital, this is the patient records, you encrypt it. Whenever you encrypt, you have to think about what key, whether this is symmetric or, public key encryption, whatever it is encrypted, but it produces a piece of ciphertext. Now, the client can produce encrypted data on their end, and then they can put it inside the virtual machine. The problem is, how do you compute on that data? If you just have to store the data, it's okay. You encrypt everything, you store it over here, you fetch it back, and then you compute locally, re-encrypt, send it back. The problem happens if you want to do any sort of interesting computations on the data in the cloud itself. So if the client wants to run, let's say, some data analytics on this data, and we will represent that data analytics operation via this function f. Okay, so you want to apply this function f on this data m, and f produces some outputs, right? um, Maybe this is an image, and you're getting a set of labels of what is there in that image, right? uh, the problem is that if you want to do any such interesting computations like this data analytics on this data, then in order to do that, you must decrypt the data on the cloud, right? If you're going to bring back the data to your own site and then apply the data analytics function, then there is no point of going to cloud computing, right? I mean, why even go to the cloud? You might as well do everything locally. If you want to do anything on the cloud and you have got your data over there in the cloud and you want to apply this data analytics function on the data, you can only do so on the clear text data. You cannot apply it on the cipher text. You only have to apply it on the plain text. So in order to do that, even if you did have your data in encrypted form, you have to decrypt the data. And the minute you decrypt the data, the cloud provider obtains access to the data in the clear, right? You cannot, so, you might say, look, there's a solution to this. The solution is I will give the encrypted data and somehow, in secret, I will give the key, then I will decrypt the data. The problem is that such solutions are non-starters, right? I mean, you cannot obtain security through obscurity. As long as the cloud provider somehow gets access to the key also, they can also decrypt the data. So there's no security through obscurity. Your protocol should all be known to both you and the cloud provider, and yet you should be able to get security on the cloud. And this solution over here is a non-starter as a result. Okay, so it so turns out that in fact, encryption is the answer, except that you cannot use traditional symmetric key and RSA like encryption that we studied in class. Rather, one solution to this problem is to use a special form of encryption called homomorphic encryption. Okay, this is not your regular encryption, it's a very special kind of encryption. Um, and this encryption, let me just very briefly tell you about it. We are not going to cover this technique in class in much more detail. It's a very special kind of encryption function, okay, which I'll denote by the script E. Of course, it's also predicated on a key, but so I'll just call it E of key. Now, homomorphic encryption has a very special property, which is that if you apply this function F to the encrypted ciphertext, right? You apply your encryption function to M, right? What do you get? You get a piece of ciphertext. This encryption is such that if I apply the function F to the ciphertext, the result that you get is the same as the result of applying F to M first and then encrypting it with that key. Okay. So as you can see, it's a very special kind of encryption. Not all encryption algorithms follow this property. So RSA is homomorphic with respect to one operation. I believe that is multiplication, but not for generic functions. So over here, if you had access to this magic sort of encryption, homomorphic encryption, you can give the cloud provider the encrypted data. You can apply the function F on the encrypted data in the cloud. The cloud provider would get this box over here, which is still encrypted, right? It's the result of some of it is still encrypted, and the cloud provider just gives you back this value, and you decrypt it locally, and therefore you get FFM. The cloud provider never sees any of your data in the clear ever. Okay, so you apply the function F on the cloud, you get back the encrypted results, and then you bring that back to your side, and then you decrypt it, you get the results of your of applying the data analytics function. Now, homomorphic encryption was for a long time just a dream, right? People wanted to implement this kind of encryption, but they had no idea, absolutely no idea how to do so. And the first major breakthrough came in 2010. It was a Stanford PhD thesis of Craig Gentry. Uh, and it was a major breakthrough. It actually won the ACM PhD dissertation award. And it took a lot of engineering to get this particular kind of encryption to work, right? It's a very deep algorithm. Now, the thing about that encryption scheme is that it's the first fully general homomorphic encryption scheme, which means it applies to arbitrary functions, okay? And it works in all cases for arbitrary f. The only problem is that this kind of encryption is still terribly slow. Right now, algorithms may improve, technology may improve, and we might still see homomorphic encryption becoming practical in our lifetime, maybe. But as of now, it's still terribly slow for most sort of uh, kinds of computations that people want to run in the real world, right? So people are working on it. There's a lot of progress every year on faster homomorphic algorithms for certain classes of computations, but as a general purpose tools, it remains uh, rather impractical uh, as of 2020. Okay, so let's look at another application setting. Okay, um, so this application setting um, is one of two mutually distrusting parties who each have some data and want to run some common function on the combined data. Okay, some analytics function on the combined data. Okay, so here's an example, right? We have two mutually distrusting parties. So there is a hospital that has access to patient data. Okay, so you've got the names of people, what disease their diseases are, what their condition is, and so on. And we will call that H. It's a database. Now, there's also a medical insurance company that probably has some insurance pricing models. Uh, I, we will call that, right? It's not a database. We can just think about it as some models. Now, obviously, these two are mutually distrusting. Now, the insurance company might have spent a lot of money to come up with these insurance pricing models and does not want to just give away the insurance pricing models to the hospital. It is not willing to share this I to the hospital. It is proprietary data of the insurance company that it cannot just share with every hospital. At the same time, the hospital is extremely sensitive about its patient data. This contains private records, private medical records, and you cannot just give patient data to the insurance company. If you give patient data to the insurance company, then the insurance company will target the people in that database and then increase the rates for those people. Right? So you don't want that either. But maybe, together, the hospital and the insurance want to compute some joint function, right? The hospitals routinely provide, anonymized data to insurance companies who can calculate, maybe aggregate rates and so on for their customers. So there is some joint function. Let's just call it script G. Uh, that the hospital and the insurance company want to compute on H and I. Um, but the problem is, as I told you, the hospital is not willing to give H to the insurance company, and the insurance company is not willing to give I to the hospital. Okay, that's the problem. So now the question is, how do the hospital and the insurance company together compute this function G? So you can, of course, use homomorphic encryption, right? The hospital can encrypt this. The insurance company can encrypt this. Perhaps they share the same kind of key and they give it to some trusted third party who then runs this computation and then gives back the results to the hospital and the insurance company. There is another very fascinating area in cryptography called secure multi-party computation that allows you to actually do this, that allows the hospital and the insurance company to uh, to compute the result of G of H of I using a series of message exchanges, in other words, a protocol, whereby at the end of that protocol, the hospital knows nothing but the output of G of HI. The insurance company knows nothing but the output of G of HI. And the hospital and the insurance company know nothing else. Okay. So this is called secure multi-party computation, or MPC. And this is a science of its own, right? It's a very deep science of its own. If you're interested in this, Professor Arpita Patra works extensively on this, right? She's been looking at this problem for like the past 5 to 6 years, and she has done a lot of interesting work in this area. And I encourage you to go and look up that work. The earliest problem, of course, in secure multi-party computation is called the millionaires problem. It's very similar to this. There are two millionaires, let's just call them Alice and Bob. Each one has access to their net assets, and they want to calculate who is richer. Only problem is Alice does not want to tell Bob how much money she has. Bob does not want to tell Alice how much money he has. But they together want to know who's richer. So they want to run the greater than equal to protocol without revealing to each other who has more money. And secure multi-party computation protocols have been developed to solve the millionaires problem, the so-called millionaires problem. That is one way to solve this problem. And there's a third way, which is to use a trusted third party, okay, or a TTP, as I will call it for short. So in a TTP-based solution, both the hospital and the insurance company would give both H as well as I to this trusted third party. Okay. So the trusted third party would run the results, the computation G of HI in a very special way. It's so-called a clean room, where the data of both of these mutually distrusting parties, hospital and insurance companies, brought in together, and the trusted third party runs their computation over there and then scrubs the result of the clean room. Okay, so when the trusted third party leaves, no trace of H or I is there. The only thing that's available is G of HI. Okay, and so the trusted third party gives the results G of HI to both the people. But the question is, in the real world, how do we find such trusted third parties? What is the guarantee that the trusted third party itself does not have malicious employees or does not have uh, a government subpoena against them? What is the guarantee of all of this? How do we find such trusted third parties in the real world? And isn't it such a painful solution each time you want to run some sort of joint computation like this that you have to approach a trusted third party? So, is there a better solution? So, that is what I'm going to talk about today, right? So, today I'm going to tell you about the Intel SGX, which is just short form for Secure Guard Extensions, which is a new technology from Intel. It's a new hardware primitive that allows you to do these kinds of scenarios that I spoke about so far. So the SGX has been available since August 2016, commercially available. If you buy a Skylake series or later Intel chipset, the SGX comes as part of the chipset. So SGX is actually a kind of trusted hardware that allows clients to protect their data on the cloud. So this is a very special kind of protection in the sense that the client's data is protected even from the most privileged software that is running on the system. In other words, the client's data is protected even from the cloud provider's hypervisor or the operating system. Even the cloud provider who controls the cloud platform on which the data is stored cannot see the contents of the data. So it's a very, very strong guarantee. So what is the SGX? So like the last class, right, when I described the TPM in terms of like the six blind men and the elephant, I'm going to give you a similar view of the SGX. Right? Uh, I'm going to first tell you what an end user of an SGX machine sees, and then we will see the inner workings of the SGX, how this end user's view is actually implemented or realized. So the end user's view is that the SGX introduces it introduces a bunch of new hardware instructions. So the hardware instruction set architecture or the hardware ISA is actually extended with new instructions that the SGX actually provides. And the goal of these new instructions is to allow the creation and manipulation of what are called enclaves in the process address space. Okay. So what is an enclave? An enclave is almost like a bank locker, right, where you can store your data, and you know the but it's different than a bank locker in the sense that you can also access and modify the data internally within the locker itself. Okay, so an enclave is a storage area where if you store your data in the enclave, it is not accessible in plain text form from either the rest of the process or even the operating system. So that's what enclave is. I'll draw a picture and I will show you shortly. So you can also place code within enclaves. Okay. And the thing is that code that is sitting inside the enclave can operate on the data that is stored in the enclave. It can this code can encode arbitrary computations, and this arbitrary computations, for example, this f function or the g function that I told you about in the previous few slides, those data analytics functions can be written as code and can be placed in the enclave. Those functions can directly operate on the data that is stored in the enclave. There is no homomorphic encryption here. Rather, it works by means of hardware, and that is what I'm about to explain. So the code in the enclave has plain text access to the data that's stored in the enclave. So any code that is sitting in the enclave can see the data in the clear. Okay, so let me summarize this in a pictorial manner. So here is a picture, okay, that shows a bunch of things. So here's the operating system on the machine. As I said, you know, if you think about the cloud, there is the hypervisor of the virtual machine. If you think of a traditional system, it is operating system and process. We'll just think about in terms of operating system and process, although the concepts carry over even to hypervisor and virtual machine. So we are looking over here at a pictorial stacked up view of a traditional computer. And we've got over here the operating system. Now the operating system manages processes. So maybe there is a process over here, and I've drawn with this box, I have shown the virtual address space of one process that is running on the system. Okay. Now sitting under the operating system is the computer hardware. In particular, over here, I have got the physical memory, and the whole machine is running an Intel SGX CPU. Okay, so as you can see pictorially over here, let's focus our attention on this box. An enclave is nothing but a linear region of the process virtual address space. Now I've shown you a picture over here where this process has one enclave. In reality, in fact, a process can have many such enclaves, but we will just focus on the setting where there's one enclave. Okay, so you can create an enclave as a linear region of the process virtual address space. Maybe you can tell the hardware, look, give me an enclave. The enclave uh, is n bytes long. Okay, and you get back from the hardware saying, okay, the enclave has been allocated at address A. Okay, therefore from A to A plus one, n is your enclave. Okay, so it's a linear region of the process virtual address space. Now, the thing about this enclave, the special thing about the enclave that the hardware provides is that, as you know, all memory is managed in terms of at the granularity of pages. Okay, so a page is 4K bytes long. Okay, so the property that the hardware gives for enclaves is that the virtual pages of an enclave are always going to be mapped to a specific region of the physical memory called the encrypted page cache, or the EPC. Okay, so the hardware provides this guarantee, provides the guarantee that all the pages of the enclave will be mapped to this particular region in the physical memory called the encrypted page cache or the EPC. Okay, so the other guarantee that the hardware gives is that the SGX CPU is going to encrypt all the contents of the data that is stored in the enclave with a key that is only known to the hardware. So that key is stored internally within the SGX CPU and is not made available to anybody, including the OS. In fact, there is no API or instruction even to go and read what that key is. Only the hardware knows the key. Nobody else knows the key. The operating system doesn't know the key. The process doesn't know the key. Nobody else knows the key. SGX, the hardware alone generates the key, and the key is stored internally inside the CPU package, and nobody can retrieve that key. Only the hardware knows the key. So the SGX CPU encrypts the contents of the data that is stored in the enclave with a key that's only known to the hardware. And it provides a property, as I will show you in the next couple of slides, it provides a property that if you have got code sitting inside the enclave, only the code that's sitting inside the enclave can access the data in the clear. So the SGX hardware will decrypt the contents of an enclave address, a particular content of the enclave is going to be decrypted only if the access to the data comes from within the enclave, code that's running within the enclave. That's why this arrow one over here, which shows that data within the enclave is being accessed by code within the enclave, that's going to be allowed. If the data access happens from the rest of the process, and the rest of the process, maybe there's a load or a store of some byte that is within the enclave, and the code that's sitting over here tries to access that, that access will be denied by the memory controller, in the sense that you will not be able to see the data in the clear. You will still be able to do it, but then you will end up corrupting the memory, but you'll not be able to actually see the contents of the enclave. Okay, it's not going to be possible. And the same thing with 3. If the operating system, remember the operating system is loaded as part of every process's virtual address space. The operating system is just part of the virtual address space. The only thing that's special about the operating system is that it runs in kernel mode of the processor. But when the operating system tries to access the memory contents of the enclave, again, that access is going to be denied. Okay, so that's what this thing over here shows, that the access 3, plain text access to the enclave from within the operating system, is not going to be possible. Okay, so one thing to note is that if you had this primitive with the properties that I've just showed you, that access 1 is allowed, access 2 and 3 are not allowed, then you can solve both our motivating problems. Both the case where you had some data to protect and you took it to the cloud, and also this case where the hospital and the insurance company want to run some shared computations. Okay, so the way you would solve the problem is that you will put your data in an enclave on the cloud provider. You will also put the code for this analytics function F inside the enclave. Okay, and you will execute this F on your data within the enclave. And you want the results, of course. So you will set up a TLS connection to the enclave, encrypted channel. Okay, and you will get the results. And the cloud provider, who is sitting over here, and also probably the rest of the process, will not be able to see anything. Neither your data, nor the code, nor the results. Everything is happening within the enclave. Same thing in the hospital and the insurance company setting. So what will happen over here is that the hospital and the insurance company together will identify a cloud provider who offers enclaves as part of their cloud offering. Okay, it's important that this cloud provider is not trusted by the hospital and the insurance company. He's not a trusted third party. It can be any arbitrary cloud provider, Amazon, Microsoft, whatever it is. No hospital has to trust the cloud provider. The insurance provider does not have to trust the cloud provider. So the way the problem would be solved is that once they identify the cloud provider, they will open up an enclave over there. The hospital will securely load H into the enclave, okay, so that it is not exposed during transmission. The H is loaded into the enclave. The insurance provider also would load I into the enclave. I will have much more to say about how data is loaded into the enclave, but bear with me for a moment. Okay, and either one of them would load the code that implements this analytics function G, and the other will verify that it is loaded correctly. And then the enclave does its job. It runs this G on the H and the I, which gives the output GHI within the enclave, and that is given back to both parties. Okay. So as I said, the important thing over here is that the cloud provider need not be trusted by the hospital and the insurance company. So even though we are identifying a cloud provider, we do not have a trusted third party who has this clean room like technology where the data is brought to this clean room, it's running over there, and the data is then destroyed and so on. The enclave provides all of those properties. Okay, so you just have to identify a cloud provider who offers an enclave based solution. Of course, I haven't yet told you how to ensure that the data, for example, H and I, and the code, for example, F and G, and so on, are loaded correctly. You want to ensure that your data is loaded, uh, that whenever you're loading the enclave with your data H, that the cloud provider does not get plain text access to H. Same thing with I. And also these functions F and G might be proprietary, right? They might be some proprietary algorithms, and probably you don't want to, give that also to the cloud provider. You can also load those in secret. And of course, you want to know that whenever you're getting the results of a computation, that you're getting G of HI, you want to know that what you're getting is in fact the output of G applied to H and I. So you want to make sure that the code that you supplied is also loaded correctly. So that particular sequence of steps to do that is actually called provisioning the enclave, or enclave provisioning. And I will tell you about how data is loaded into the enclave, how data is provisioned to the enclave towards the end of today's lecture. Okay, we will first focus on how the enclave technology uh, is enabled. We'll show you how you can actually perform computations on data once it's been loaded. Okay, so in the next few slides, I'm going to make the assumption that the data is already loaded in the enclave, that the code is already loaded in the enclave. And then I will tell you how the computation remains secure. And towards the end of the lecture, I'll tell you how the data is loaded into the enclave securely. And I'll give you a hint right away. Maybe you can pause the lecture and think about it. So the act of provisioning securely actually is very closely related to the last lecture on attestation protocols. Okay, so using attestation, you can actually build such a enclave provisioning system. And I will describe that at the end of the lecture, but you might want to give it some thought, just as a fun exercise to stretch your brain and see whether you've really understood how attestation works. Okay, so what I have described to you so far actually sounds like magic, right? You can take your data, nobody sees the data, it's running in the cloud, it's stored in the cloud. You have got some code, you don't want to show that code to the cloud provider. You somehow send it off to the cloud provider, they are unable to see the code the clear. The code operates on the data, gives you the correct result. The cloud provider doesn't know what it is, but you're able to see it. It seems too good to be true. Okay. But this is possible with the SGX. Okay, so let us see how. So on a traditional normal CPU, right, the way that things work is that the CPU has two processor modes, right, which we have already studied when we looked at the lecture on virtualization, right? The two modes are the kernel mode and the user mode. Kernel mode is often called ring 0, user mode is called ring 3. Okay, so and the state machine over here shows how you transition between the two modes, right? So when you are in user mode, the way that you invoke the kernel mode is via system call, or actually a trap into kernel mode. And the kernel actually does some things, and then the return from syscall returns back control to user mode. So the idea is that the processes typically run in user mode, and whenever you want to invoke some operating system services, you go to kernel mode. The kernel mode is supposed to be the more privileged mode where you have access to certain registers, certain data structures that you don't normally have access to within the user mode. And that's determined by the Popek Goldberg virtualization criteria, if you remember that lecture from virtualization. So the kernel mode is all powerful and it has full access to the virtual address space of every process. And that is why the kernel mode, you can actually see everything going on in user mode. So the SGX actually makes a fundamental change to this particular state machine. Okay. So within the user mode, right, what it does is that it actually introduces now, it becomes a three-state machine. Then you have something called the kernel mode. Actually, this is just a simulation of the operation of the SGX. You have a kernel mode, you have the user mode, and you also have a so-called enclave mode of execution. So the user mode to kernel mode transitions are as in this diagram. User mode goes to the kernel mode via syscall, return from syscall from the kernel mode gives control back to user mode. Now, to enter the enclave mode, the hardware actually provides a new instruction called EENTER. So if you're in user mode and you execute the EENTER instruction, you enter the enclave mode of the processor. You can actually you enter a pre-created enclave at a fixed entry point, and exit executed in enclave mode goes back to user mode. You cannot execute EENTER in kernel mode; it's not possible, and you cannot execute EEXIT in user mode and go anywhere. These instructions have to be executed from the corresponding modes. Otherwise, you'll get an error. So importantly, you cannot go directly from the kernel mode all the way to the enclave mode. There's no way. You have to go via this user mode. And likewise, from the enclave mode, you cannot directly go to kernel mode. You have to go to user mode and only then to the kernel mode. In particular, you cannot make a syscall from the enclave mode. You have to go to user mode and the syscall has to happen from there. Okay, so the thing is that the kernel mode and the user mode, if you have code that's running in kernel or user mode, the SGX ensures that they do not have plain text access to the virtual address space of the enclave. If you have to be able to access the virtual address space of the enclave, you have to be in the enclave mode of the processor. That's the guarantee that the hardware actually provides. So here is how that is implemented. So as you know, a process, a virtual address space is divided up into pages. So I've shown here a simple picture of a virtual address space that has 8 pages. Okay. And let us just say that this particular process over here designates 3 of its pages to be part of one enclave. Page V3, V4, and V5 are part of an enclave. Okay. As I told you, the hardware ensures that enclave virtual memory pages are always backed in a particular region of physical memory called the EPC. So let's draw physical memory over here. I've just drawn a very simple picture where the number of page frames in physical memory is equal to the number of page frames in virtual address in the virtual address of this process. You obviously know that that's not the case in machines. Um, but I've also depicted the EPC over here, three page frames. Okay. In a real system, the EPC is around 128 megabytes of memory. There's 128 megabytes that's reserved for the EPC, an SGX version 1. Uh, and as you know, the operating system manages the page table. Okay, so over here, because the EPC has to map the pages of the enclave, you can see that page V3 is mapped to page P7 in the enclave. Page V4 is mapped to the EPC page P6, and page V5 is mapped to EPC page V8. Okay, P1 is mapped to some P4 that's not in the EPC. V2 is mapped to some P3 that's not in the EPC. Not every page in the virtual address space of a process needs to be mapped, but dot dot dot, right? More such mappings exist. And the operating system manages these mappings via this data structure called the page table. Now, the way that the SGX is implemented is that the hardware, the SGX hardware, ensures that the enclave virtual pages are only mapped to the EPC region of physical memory. The memory controller actually ensures this. So when you create an enclave in a process virtual address space, the processor is aware of exactly which virtual memory pages correspond to enclave pages. And whenever there is a memory access that the memory controller now tries to direct to a physical page, it knows that that page is an enclave page and it checks that the corresponding mapping is going to the EPC. If it is going to a non-EPC page, immediately there will be a hardware error that prevents that thing from happening. Okay. So the important thing to note over here is that this page table over here is a data structure that is managed by the operating system, which in SGX model is untrusted. In fact, it could even be malicious. The operating system could be actively malicious and try to change these page table mappings that are part of the page table and try to defeat the security guarantees of the SGX. Okay, so the operating system could even be adversarial, but it does not matter because it is the hardware that is performing the check and ensuring that the virtual addresses that are coming from the enclave only go to the encrypted page cache, nowhere else. They cannot go to the rest of memory. So that is how you ensure that the enclave is protected, by always ensuring that the corresponding memory that backs it is always encrypted. So the other guarantee that's provided is that whenever there is a memory access that happens to a byte that is stored in pages V3, V4, or V5, which are part of the enclave. So whenever I say memory access, I mean a load or a store instruction. Whenever a load or a stored instruction tries to access the contents of pages V3, V4, and V5, the processor immediately checks. Okay, in other words, the memory controller requests the processor to check. Is the processor running in enclave mode, which is this third mode of execution? Are we in the enclave mode of execution? And if the answer turns out to be no, then, well, the processor is either user mode or in kernel mode, and therefore it's either kernel code or user code trying to access the enclave. And so the view, the contents that are presented to that load or store will be the encrypted view. That is just the encrypted contents are presented uh, to that load or store. In fact, it's not the encrypted contents. There's another logic that presents just zeros or all Fs, but it presents, you can think about it as it's presenting, it is not presenting the plain text. Okay. And if it so turns out that the access is in fact a yes, the answer is in fact a yes, that is, the access is happening, a load or a store is actually happening from within enclave mode, which means that code that is sitting in one of the pages v3, v4, or v5 is trying to access data in pages v3, v4, or v5. Then what happens is that, as you know, whenever you try to access data from memory, memory is brought into the cache, and all data access happens within the cache. That's the cache hierarchy. So what happens is that the processor brings data from the EPC to the cache line, which is sitting inside the CPU package, and it decrypts the data with the key that the hardware, knows. Right? Remember, the CPU over here is the hardware. CPU is managing the keys, and the CPU is bringing the data from the EPC to the cache line. And because it knows the key, the CPU knows the key, it can actually decrypt the data and therefore provide clear text access to the data that's stored in the enclave to the code that is also running within the enclave. So therefore, enclave data can be accessed in the clear by enclave code. And so whenever you finish your computation on that particular cache line, if that cache line has to be evicted, the hardware re-encrypts that cache line and then sends it back to the EPC. So the data is not even going to be traversing in the clear on the memory bus, right? Even the memory bus. So you have to think about a very powerful attacker in this case, right? You have to think about an attacker who is not just controlling the, let's say, operating system or the hypervisor. The cloud provider has access to the physical infrastructure as well. And a determined cloud attacker, an adversary in the cloud, can actually go and insert probes on the memory bus and tap every bit that is uh, traversing the memory bus, which is the interconnect between the physical memory and the CPU package. And SGX ensures that data that is backed up, the physical memory that is backing the enclaves, even that physical memory is never the contents of that physical memory are never revealed in the clear, even on the memory bus. So even when this data over here is traversing its way to the CPU, the data is going to go in encrypted form. The decryption, actual decryption, only happens within the CPU package. So that brings me to a very important point. In the SGX, the threat model is that you trust nothing but the CPU package. You don't even trust the other hardware that's on your chip. For example, the memory and so on is not trusted. You only trust the CPU package. The CPU package is the only one within which the data will ever be in the clear, and the key is managed by the CPU. Okay, very, very, very powerful threat model. Okay, so to summarize, the kernel code cannot access the enclave. The process itself cannot access the enclave. And in order to access the enclave, the you must execute EENTER, which you can only do if you're running in user mode. And that takes you to code that is executing within the enclave. So only the enclave code can access the enclave data. Okay, so that is what SGX provides. All right. So if you have followed the discussion so far, we have actually entirely solved the problem of secure data access on an untrusted cloud provider using the SGX. But all of this assumed, of course, that your data is already loaded into the enclave and your code is already sitting inside the enclave. I haven't yet bootstrapped the problem. I haven't yet told you how to bootstrap the whole setup. That is, how do you get your data into the enclave in the first place? I haven't yet told you that. So, in other words, provisioning. That's what we are going to be looking at now. So, let's look at some strawman solutions. So can you encrypt the data and send it to the enclave? Right? Maybe you are the client, you're going to encrypt it somehow, send it to the enclave. So the answer is possibly, right? You can probably send the data and you can send it to the enclave if you have some way of decrypting it in the enclave. Now, if you have to decrypt it in the enclave must have the corresponding key. But how do you get the key to the enclave? Okay. You cannot give the key in the clear to the enclave, because if you give it in the clear, the cloud provider can observe it and therefore decrypt any encrypted data you send as well. So if you think back to our key exchange protocols, maybe you and the enclave can engage in a Diffie-Hellman key exchange and therefore generate this key that you're going to use for your encryption via this Diffie-Hellman key exchange. But remember that even the Diffie-Hellman key exchange at its heart was a public key-based scheme where there were some public parameters. And those public parameters also need to be certified. Otherwise, you have a man-in-the-middle attack. So the public parameters of the Diffie-Hellman key exchange, as long as there is no trusted certifying authority saying that that's the key, you can't really um, engage in a Diffie-Hellman key exchange because there'll be a man-in-the-middle attack. Okay, so you and the enclave can't just engage in a Diffie-Hellman key exchange because the key of the enclave has not been certified. If the enclave has a key, a public key. Okay, so this bootstrap problem, it so turns out, can be solved using a very clever method uh, that again boils down to trusted hardware. Okay, so it turns out that the SGX also provides TPM-like functionality. I won't say exactly like the TPM, but very much like the TPM. Okay, so the SGX hardware, every chip has a public and a private key pair. Now, it is very important to remember this public-private key pair is just the identity of this hardware. It is not related in any way to the key that's actually used to encrypt the contents of the enclave. In other words, this content over here that is stored encrypted in the EPC, it's not that public-private key that is used for this encryption. That's another hardware managed key. Okay, so this key pair that I'm talking about over here is different from the one that is used to encrypt the enclave contents. Those are actually ephemeral hardware generated keys. So the public key of an SGX chip, it is actually digitally certified by Intel CA. So there's a trusted certifying authority that's actually providing you a digital certificate for the public key. And in some sense, this private key is actually hardwired into the chip itself. So it's in some sense burned into the silicon. It's there as part of the circuitry. So whenever there is a request to create a new enclave, and that happens via another hardware instruction called eCreate. By the way, the hardware, uh, the API, the instruction set architecture, it has around 20 instructions. I have only told you about 3 so far, which is e-enter, e-exit, and I'm telling you now about eCreate. There are many other instructions as well, but I'm trying to keep the lecture at a level that is that allows me to explain the concepts without actually delving into the details of every instruction. Only where absolutely required, I'm presenting those instruction names. So eCreate is the hardware instruction to create a new enclave of some particular size. And the idea is that whenever the eCreate instruction is provided, the hardware creates an empty enclave, okay, with some really bare minimum code to do some crypto operations. Okay, and what that does is that it brings up the enclave and it generates a public-private key for the enclave. We'll just call that pubenc and prevenc. Okay, and the prevenc is stored within the enclave. So the nice thing is that now you have this hardware primitive called the enclave that provides you security from even the cloud provider. You can store your data over there, secret data over there. It's not visible to the cloud provider. So the private key of the enclave is stored within the enclave and it's not visible to even the cloud provider. Okay. The public key is made part of the enclave creation report. That is, when you create an enclave, as you will see in the next slide, you actually get an attestation report that is publicly visible for everyone to see. The public key of the enclave is made part of this enclave creation report. Okay, so the public key of the enclave is therefore available. The only thing is that I haven't yet told you how it is certified. I will tell you that in the next slide. So the client actually requests an attestation report to make sure that the enclave creation happened properly. So the cloud provider executes the create instruction, but it does so on behalf of the cloud client. And so the client will actually want to make sure that the cloud provider has done a thorough job, that the cloud provider didn't cheat, and so on. And so it requests an attestation report to ensure that the enclave was created properly. Now, this is exactly identical to the problem that we discussed in the last lecture. The cloud provider is making some claims, right? In this particular case, it's making the claim that the enclave started properly. How does the client go about verifying it, right? That is exactly what we invented or we developed attestation protocols for, right? So the client is now going to request a very similar kind of attestation to ensure that the enclave was created properly. So the SGX hardware actually provides this attestation report. And this attestation report is digitally signed by the SGX hardware's private key. Remember, this SGX hardware's private key is different from this Prevenc. This Prevenc is a key that is stored within the enclave for communication within the enclave. The hardware's private key is different from this Prevenc. This Prevenc is a private key that is provisioned within the enclave, so it's stored in software. Whereas this digitally signed hardware private key, this digital signature, which is signed by the hardware's private key, is actually signed by the hardware's key that's burned into the hardware. So there's a bunch of keys that's at play over here. It is this public-private key of the enclave uh, that the client uses to communicate with the enclave. There's a key that is used to uh, encrypt the enclave contents. That's actually a symmetric key that's ephemeral, that's managed by the hardware. And there's a third set of keys that is the public-private key of the SGX hardware. So when you are actually sitting and reading this stuff, please don't get confused. There's three kinds of keys that I've spoken about so far. Don't get confused. Uh, to repeat again, the first pair of keys is the hardware's public and private key that's actually burned into the hardware itself, where the public key is certified by the Intel CA. There is another public private key that is generated whenever a new enclave is created. The public key is made part of the enclave's creation request report, and the private key is stored within the enclave. And the third is the key that is used to encrypt the enclave contents. That's an ephemeral symmetric key. Okay, so three sets of keys I've told you about so far. It's more complex than this if you look at the real implementation, but I'm just giving you these three keys. Okay, so this attestation over here is conceptually similar to the TPM based attestation. So I will refer you back to the last lecture. The only differences are low level details. There is no concept of a PCR register in the SGX, and there is no TPM extend operation. But intuitively, it's the same, right? I mean, what did the TPM do? The TPM had a way of measuring the software uh, that was just booted in that case and giving you an attestation report. Over here, the hardware has a way of measuring the newly created enclave by actually looking at the EPC page contents and providing an attestation report. Okay, so conceptually it's similar, even though the specific details of how the attestation is implemented are different. In the case of TPM, it was PCR registers and TPM extend. In the case of SGX, it is different circuitry. Okay, but the idea is that the hardware is able to measure what was created and provide an attestation report, again a hash of uh, the software that was just created as part of the enclave. Okay, so as I told you, because the public key of the enclave is part of the enclave's creation report, uh, the public key is also digitally signed by the hardware's private key as part of the attestation report. So therefore, you find that as a chain of trust, the enclave's public key is also indirectly certified by Intel CA. And so that is why whenever a public key is provided for an enclave, that key automatically comes digitally certified. So now that you have a public key that is certified for the enclave and the private key stored within the enclave, the client can actually engage in a TLS handshake with the enclave. Okay, remember TLS handshake from many lectures ago? So you can engage in a TLS handshake with the enclave uh, and therefore create an end-to-end encrypted channel all the way from the client's machine to within the enclave. So now the client can send its code and data to the enclave and then provision the enclave securely. You will note that everything is encrypted all the way from the client's computer to within the enclave. Now, whatever code and data is sent by the client is decrypted within the enclave, but it's invisible to the cloud provider anyway. Once it's sitting inside the enclave, it's invisible to the cloud provider. All right, so that brings us nearly to the end of today's lecture. SGX supports way more features. It supports this concept of sealing, which is you can actually bind data to a particular physical computer. But we are not really going to talk about that in today's lecture. So the assigned reading for SGX, the first set of readings is actually the original paper from Intel that talks about the SGX technology and the basic features, the new instructions and so on that are used to implement the features that I spoke about today. Now, SGX is not without its shortcomings, right? There are plenty of shortcomings. In fact, the biggest shortcoming is, of course, developing code for the Intel SGX platform. You cannot just take an application from off the shelf and run it. The reason is because if you're sitting in enclave mode, you cannot make system calls, right? Any interesting software makes system calls. And so now if you have to make a system call, the enclave must have a wrapper that does an e-exit, performs the system, goes to user mode. User mode performs the system call on behalf of the enclave. You get a return value from the system call and then you return it back to the enclave. Okay, so porting code is a big problem, right? The enclave does not allow system calls to execute directly from within. So that opens up an attack channel. Also, remember our trust model is that the enclave is running the trusted code of the client. The user mode, the kernel mode are all untrusted and can potentially even be adversarial. So if the user mode code is going to be performing system calls on behalf of the enclave, maybe the user mode, the kernel mode can somehow collude and then use the system call as an attack channel to fool the enclave or to get the enclave to misbehave or to spill secrets or not do things properly. And that's possible, right? The system call over here, because it's being executed by user mode, you have to make sure that the results are correct and the enclave is actually getting the correct results of the system call. Okay, and that is a big problem. The system call return values become an attack vector. And we will see a detailed discussion of this attack vector in the next class when we see an application of the SGX to containers. Okay, so I'm going to be talking about this paper called Scone that builds on top of the SGX and provides security for containers, where they also provide protection from malicious system call return values. So the third attack are side channel attacks. And these stem from the fact that the page table, which maps the page frames over here in the virtual address space to physical memory, The enclave pages are mapped to the EPC by this page table. And I already told you that the hardware ensures that all enclave pages are only mapped to the EPC. Hardware can ensure that, memory controller can ensure that. And that is provided by the hardware. But what the hardware cannot do is to stop the OS from observing the page access patterns, right? It can clearly see that the enclave is currently accessing V3. Then maybe the access goes to V5, and then maybe the access goes to V4. And there was a very clever sequence of attacks, side channel attacks, that were published around 5 years ago, where they showed that software has unique access patterns. And by studying the access patterns, you can figure out what the software is doing. Okay. So through that indirect channel, people were able to leak secrets from the enclave. Okay. And so this page access pattern is visible to the underlying operating system. The reason is because the underlying operating system manages the page table. And these side channel attacks are a real threat vector in the case of the SGX. We are not going to be studying defenses against that. In my own lab, we have developed defenses against side channel attacks of this sort. A lot of other people have also developed side channel attacks against this. I refer you to, for example, the SGXL paper from our lab to see one possible defense against side channel attacks. But I will not be discussing them in detail. We'll be talking about other kinds of side channel attacks, two lectures from today. In particular, things like Meltdown and Spectre. But I'm not going to be talking about them, about SGX side channels anymore in this course. All right, so that brings me to the end of today's lecture. So in summary, the SGX actually provides a big leap forward in enabling secure cloud computing, where the scenario is this: the cloud provider is untrusted and could in fact be malicious. And the cloud provider therefore should not be provided any access to confidential client data. Yet the client should be able to compute on that data. And that is what the SGX makes possible. So as I already told you, the SGX has some shortcomings. Porting code is a problem. The page table is managed by the OS. That's a problem. And as security is always a cat and mouse game, right? Intel came up with this technology. They thought it was very promising. And in fact, it is. It's an ingenious technology. But the attacker community, which is a security community, has also thought about very clever attacks that Intel could not foresee at the time. And therefore, the SGX suffers from a lot of these shortcomings. And Intel has responded by coming up with the next generation of technology. That generation of technology is called TDX, or Intel Trusted Domain Extensions. The white paper is available. The hardware is going to be released soon. As of today, which is December 2020, this hardware is not yet publicly available. There's a very similar technology available from AMD that's already publicly available. It's called AMD SEV, or Secure Encrypted Virtualization. And TDX, at least based on my understanding, appears to be very similar in terms of functionality to AMD SEV. And TDX is due to be released in a future generation of processor.